DC motor as commutator and brush mechanism to supply a DC voltage, appropriate DC voltage, current direction to the armature coil. Otherwise, DC motor won't work. Every 180 degree, you have to change the polarity of the voltage applied to the armature coil. That is done by the commutator. It is a mechanical device with brush mechanism. That's how the DC motor works for last 150 years something. But the major problem is wear and tear of the brush, physical contact brush on the commutator. Commutator made out of brass or something material, conducting material. Commutator generally, brush is made of carbon brushes. You know the carbon when contact, they're a good conductor, but quickly they worn out. So frequently you have to replace brushes. After some few years, something, if they continue operating, you have to change the commutator itself. That means changing commutator not easy. Cut physically, mechanically, you have to cut and remove it again, weld, brazing, all those things. That is not this one. So these are this one. So they come out with BLDC motor in which the rotor is a permanent magnet. Armature, nowadays, the BLDC motor called as a rotor. Rotor is made of permanent magnet. So there is no need to supply voltage, no brushes, no commutator. The bad effect of commutator, giving spark, EMI not generation. And if it is a explosive environment, the spark can create explosion, fire action. All these things are removed by using BLDC motor. Mechanically advantage, no friction, correct? No wear and tear. Maintenance is easy. All those things, that is BLDC. But even though removing the commutator and brush mechanism to the armature, which is electromagnet, previously in DC motor, in electromagnet, now it is a permanent magnet. Advantage, but problem is the stator voltage you cannot supply DC voltage. Correct? Armature is now we call a rotor. Rotor is a permanent magnet, no voltage, nothing. Very simple. Advantages there, commutator. But stator mechanism to make the rotor, the permanent magnet rotor, to rotate clockwise or anti-clockwise direction, you need to supply not a DC voltage. You need to supply a sequential voltage. Instead of DC voltage, you supply a sequential DC voltage as a pulses. Correct? On or off. It is called as on-off pulses. You supply the voltage to the but again, I told you that in brushless DC motor, field coil is not a single coil. It is made of 3 coils. I called as a coil A, coil B, coil C. Like a AC motor, it has a 3 coil, not a single coil similar to a field coil in case of DC. So that is another difference, correct? Stator, which is nothing but equal to field coil in a DC motor, is made of 3 coils and it has 3 stator poles on which the 3 coils are wound, and you need to supply the DC voltage, sequential DC voltage to all 3 coils in particular sequence and particular voltage level. That's what we will be talking, right? So that means you need to generate this voltage from the battery. Even please note that we need a DC voltage, so it can be a battery or DC power supply by BLDC. From that, you need to create these waveforms, correct? Dry waveforms for each stator phase. So one after another with a 60-degree phase shift, you have to create the voltages and supply to the 3 coils one after another. So which creates a magnetic field. That magnetic field will attract the rotor. So the rotor rotates from one pole, stator pole, to another stator pole, another stator. That means you switch on at a time 1 or 2 poles at a time. So that means you need to create waveforms, square type waveform, which will be supplied. Because of that, many times the people call it a trapezoidal waveform. Correct? The shape of this one is trapezoidal waveform. Need to supply, or many times you can supply modified square wave. We are going to see that. Correct? That will induce current, which is a trapezoidal in nature. Because inductor is a coil in which even if you supply a square waveform, the current will be in the shape of trapezoidal, because be inductive of a RL effect is going to do that. So we need to supply voltage. So that means we need to generate voltage. So even though we are avoiding commutator, brush mechanism, wear and tear for all those things, in a brushless DC motor, additional burden is there. rotor becomes simplified, armature becomes permanently simplified. But the stator, you cannot supply just a pure DC DC field coil. Here, stator, you should supply a time varying voltages to 3 different stator coils, one after another particular sequence. So there's some complication, but this has advantages. Even though we have to generate voltage, all those things, but still it is much better than a brushed DC motor. Correct? And already yesterday we talked about commutation, because supplying voltage at different time at different phases. Coil A, 3-phase coil to a DC motor is called as commutation. This is called as electronic commutation instead of mechanical commutator DC motor armature. Here the stator coils are supplied with different voltage level. 0 volts or full voltage for a certain duration of time. So there's a trapezoidal current flows there, which creates a magnetic field. That magnetic field get locked with the rotor magnet. So since you are giving a sequential, the A, B, C, this is A, B, C. This is magnetized, this attracts. Next, this is magnetized, this attracts. Then this is magnetized, this attracts, one after another. Simplified version, correct? So that the rotor rotates. We are getting mechanical motion and the interaction, magnetic field interaction between the stator coil magnet and permanent magnet rotor generates a torque. That is what called that torque is used for driving the load, correct? So now commutation achieved electronically, which is nothing but in case of BLDC motor, commutation means supplying stator coil with voltage levels at appropriate time in a particular sequence. We are going to see that to achieve the commutation as a continuous rotational rotor, the stator windings are energized in the sequence as I mentioned first step, and the position of the rotor is noted, correct? I told you we are going to supply, for example, coil A is energized with a pulse at T equal to 0, correct? Maybe for example 10 milliseconds or 100, for example I'm saying, correct? That depends upon 120 degree or to this one. Now the rotor is rotating, attracted by this magnet. Stator magnet attacks the rotor magnet. So because of that, rotor rotates. Rotor will rotate 120 degree and will stop, and will come and align and stop here. It won't rotate further. If I want to rotate further, I will switch off this, I give voltage here. So from here, this is rotated by another 120 degree, correct? So then switch off this, give you a voltage to this. So this is all for every 120 degree once, we are going to supply voltage to the coil A, coil B, coil C, so that the rotor rotates 360 degree. So again, we repeat the sequence. That sequence is repeated. But how do you know the rotor is rotated to the aligned with this coil, first coil? That means we need to know that current position of the rotor. Because rotor has 2 poles, north and south poles. Because generally we use a sensor which is called a Hall effect sensor. Already told you, Hall effect sensor is used to sense the north pole of the magnet. Correct? I put a north pole here, for example, Hall effect sensor. For example, this is a HA sensor, Hall effect sensor. Now the rotor is rotating. Correct? The rotor is currently aligned like this. This is the rotor phi R. Correct? North. Okay. Now it is rotating when it aligned like this. Correct? As it moves, rotor is rotated, attracted by this pole. The magnet, rotor magnet aligns like this. Correct? That time it will generate a pulse. When the north pole comes near the Hall effect sensor, it generates a pulse. How long the pulse will there? As long as north pole is there, it will generate a pulse for some duration. Till the north pole crosses this area. Correct? Till the north pole. This, as long as this is within this, since my HA is here, during this entire duration, the sensor will generate, for this 120 degree, the sensor will generate a pulse, Hall effect sensor output, Hall sensor output, 120 degree period, because during this period, north pole is facing, correct? The magnetic flux will go and touch. So it senses. Now, if the rotor rotates, something like this, this is my north pole, correct? This is my south pole, bottom side is south pole. So that means this will not get, there is a Hall effect sensor, HA sensor 2. This will provide, yes, so this one, this is for 120 degree. correct? For 120 division, it will give a pulse source. I will sense this one, correct? This Hall effect sensor voltage is given to the controller, microcontroller, which is programmable, which is going to generate the voltage to the coils. Coil voltage is generated by the controller based on the Hall effect sensor. Correct? There are 3 Hall effect sensors. This voltage will be used as input to the controller, which will generate the stator coil voltage and apply sequentially. Because now we know that now it becomes a closed loop control. Correct? The sensor is sensing. As long as the rotor is north pole is within this angle, the sensor gives a pulse. During the time, this is energized and others are not energized. Simple sequence. But many times, we are going to see that today, the 2 poles of the stator coils will be energized at a time, so that the 120 degree, this one is completed, a smooth torque is generated. More torque is generated because the 2 magnetic, one is attracting, one is repulsing. So together they produce more torque on the shaft. Correct? Shaft torque, T shaft will be higher. One will be pushing, other one will be pulling. We are going to see that. So those voltages are generated by the microcontroller or the BLDC controller by sensing where the current position of the rotor using Hall effect sensor. Correct? So already told you we need 3 components. One is a rotor position sensor, generally Hall effect sensor. This signal is given to the voltage generator, coil voltage generator, which will generate one after another sequentially. Control signal is the rotor control signal generated based on Hall effect sensor. The BLDC motor uses Hall effect sensor embedded in the stator to sense the current position of the stator. Already I told you. Already I told you there are 2 types of motor. One is the in-runner motor. That means rotor is inside and rotating, or rotor can be outside also. Body, inside the body, but outer circumference, the rotor which is rotating, your stator coil will be in fixed position inside. This is called outrunner type motor. This is called in-runner type motor. BLD both are available. Depending upon application, power, and this one, you can select any of this one. Okay. Already I told you that 3 coils are energized, one after another, particular signal. See, this is on, correct? Up to this period, only the coil A is on. Remaining 2 coils are off, correct? Then this also on. The second coil also started on. After this time, the first coil, A coil, we call it A or B or phase 1, we can call it. We know that the voltage becomes 0, but B coil still power is there. But after some time, C coil comes in picture, kicks in. Correct? You can see that this is called overlapped. Correct? It is not one after another. Correct? Simplest thing is will be like this. You can do like this, one after another. But instead of that, many times, one coil is on, it may be attracting the north pole. For example, this is the south pole. Correct? This is the north pole. I applied a voltage. Correct? I applied a voltage. North pole, this is south pole, this attracts, correct? So this is magnetic, it attracts. By that time it comes and aligns something like this, correct? And you will energize other pole, correct? This pole will become south pole, and this also will become south pole. So this will attract further, because north pole of rotor will be attracted. So by simultaneously, and this is called an overlapping area. Correct? This is the overlapping area. Correct? By overlapping, what we are doing, there's a continuous torque production. So smooth running of the rotor happen, torque production will be better. Correct? Instead of sequence you doing, little bit overlapping is done. That's how it works. We know that torque produced by the motor, I already told you, this is the magnetic flux of the stator winding, which is the electromagnet. Phi r is the rotor, which is the magnetic flux strength. Sin theta is the angle between the magnetic axis of the whichever coil is magnetized. Correct? This is the magnetic axis, and this is the stator axis. This angle is called theta. Sin theta of that, if you multiply, you will get instantaneous, because as the rotor moves, the torque is not going to be a constant. Correct? It will be varying with this one. We are going to see later. Correct? Okay. Now that as I told you, we need to drive the coils one after another sequentially, like by generating this voltages and which will apply to coil because the current flows because of the magnetic flux created in each phase. Correct? That's how it works. So now going to further dwell deeper into this, how to drive a BLDC motor. Correct? BLDC motor is similar to, if you see the functionality of BLDC, it is similar to permanent magnet synchronous motor. Already we talked 3 to 4 classes, previous classes, correct? So in which you have again exactly same as the BLDC motor. It has a 3 stator coils supplied with 3-phase AC voltage. We are going to, there we supplied AC voltage, correct? We supplied with AC voltage, 3-phase AC voltage we supplied. This is phase A, correct? PA, PB, PC, but thing is the stator coils are supplied with the AC voltage. Okay. And again, there's a rotor is a permanent magnet. In case of BLDC motor, the stator will be not supplied with the AC, sinusoidal. AC voltage means I'm talking of sinusoidal voltage, will be supplied with trapezoidal current. We supply a square wave, but because of that, current flowing inside will be a trapezoidal inside. The current supplied to the coil will be trapezoidal, but voltage applied will be square wave. Because of the inductive RL effect of the coil, the current flowing inside the stator coil will be trapezoidal in nature. Instead of supplying a sine wave, we are supplying a square wave which generate a trapezoidal voltage or trapezoidal current flowing inside the stator coil. Correct? Whenever voltage is applied. So why we have to do trapezoidal? Because I told you when we talked about 2 type of permanent magnet motors are there. Synchronous motor. One is called as distributed winding. Other one was called as, what is the other name? Any idea? We have talked about it. Here also it is mentioned. Other one is called concentrated winding. Correct? So the BLDC motor uses concentrated winding. Permanent magnet PMSM, permanent magnet synchronous motor uses sinusoidal excitation and it uses distributed winding. Because of distributed winding, when you supply a sinusoidal AC voltage each coil at any given instant, the magnetic field created also will be in the shape of sine wave. Because of that, the permanent magnet synchronous motor generate a smooth this one torque curve, flat torque curve, because one after another you are exciting, because sinusoidal nature they are overlapping each other one after another. So permanent motor synchronous motor generates a smooth torque, but the torque produced will be for the same winding, same amount of current and voltage. The BLDC motor generates a higher torque, but only thing is at low frequency, because we are supplying a trapezoidal voltage, trapezoidal current to the coil, instead of supplying a sine wave, the torque will be pulsating, little pulsating at low frequency operation. This BLDC motor will be, for example, I'm talking 500 RPM, 100 RPM, 200. If you run that, there will be a torque fluctuation. There will be a slight vibration which is not needed. If you want very accurate, smooth, this one you should go for permanent motor signal because it is supplied with 3-phase AC sine wave. Okay, that is one difference. So since our coil, another thing is in permanent signal distributed winding. If you supply AC voltage, sinusoidal voltage to distributed winding, the distribution itself called a sinusoidal distribution. Permanent synchronous motor is called distributed. The winding type itself called as sinusoidal distribution. That means the magnetic field created in the air gap will be very smooth. Already we discovered that. So, but the torque will be less, smooth torque curve and all those things that is better, that is drawback. But if you want more torque for the given voltage and this one, you will go for BLDC motor, and the BLDC motor creates a little ripple, torque ripple when you operate low frequency. So when you go to high frequency, the ripple will not be there, it will be automatically taken by mechanical. Inertia, rotor has inertia, bearing friction, all those things works as a low pass filter. They remove minor for this one, you will get a smooth curve even in the BLDC motor. So BLDC motors are used for high speed operation. Low speed operation, you generally, if you have a smooth operation, you will go for permanent magnet synchronous motor. Okay. So the stator winding is wood in the patient of trapezoidal patient. not which is called a concentrated winding. So if you give a square wave, the current flowing that will be trapezoidal, and also a back EMF is generated. Correct? Already told you synchronous motor, the permanent magnet synchronous motor, the rotor is rotating. The magnetic flux of the rotor is cut by the stator coils. Correct? Because of that, there's a back EMF voltage is generated. That voltage in the synchronous motor also will be sinusoidal nature. In permanent magnet synchronous motor, the back EMF, correct? Back EMF will be in the shape of sinusoidal because the coils are distributed winding. But in case of the BLDC motor, the winding, stator winding itself is a trapezoidal pattern, which is called a concentrated winding. So the magnetic back EMF produced by the windings of the BLDC, stator coil will be in the shape of trapezoidal nature. So that means, again, why it is that means, if you supply a trapezoidal voltage to the coil, correct? We are talking about trapezoidal voltage will be something like this. This is the coil supplied to phase A. I say IA current, correct? This is the supply to coil A. The back EMF also should be same. Then only maximum torque will be produced. So that's why in BLDC motor, the stator coils are wound in a trapezoidal pattern, which is called as concentrated winding, for which the current supplied IA, which is supplied by the controller, motor controller, we have to generate a voltage, and which the controller back EMF. Why? Become a generator. That means, please note that in case of BLDC motor or permanent and synchronous motor, there is a applied voltage which is sinusoidal nature. So current is sinusoidal. The back EMF generated due to the rotor magnet, because rotor is rotating. It works as a generator. That will be in the other sine wave. So the difference in voltage is called driving voltage. Correct? We know that if you have back EMF is always negative. Correct? It will be negative compared to applied voltage. Applied voltage is positive, means the back EMF will be negative. So the difference will be, correct, will be the final voltage applied in the stator coil, because of then that voltage divided by impedance of the coil, the current flowing, that will be called a resultant magnetic flux. Pi R, IR is resultant current. We can say that VR equal to V supply minus V back EMF. Okay, already we talked about DC motor. If you remember 10-15 classes we will talk. Correct? This is the net voltage in the stator coil. This is generated because of the rotor magnet. Rotor magnet is rotating and it is a permanent magnet. That flux is cut by the stator coil. So there's a voltage induced in the stator coil. All three stator coil producers. I say the VA back EMF. This is VA supply voltage. VA supply voltage minus back EMF divided by Z will be the current flowing to the coil. Correct? So this is called resultant voltage. Supply voltage minus back EMF is the resultant voltage. This voltage divided by Z will be the resultant current. Because of resultant magnetic flux, I can say the small r, because rotor. So this resultant magnetic flux is get locked or pulls, attracts, locks or attracts the rotor magnet. So that is, I say phi r. Phi r will be get connected with this. So next phase, the rotor will rotate. This will happen. Correct? You understand? I think that's why I'm explaining. So the shape of the back EMF determines what type of input drive should be given. If the synchronous motor and if it is distributed winding, the rotor, the stator should be supplied with a sinusoidal voltage. The rotor will generate a sinusoidal back EMF. So the net voltage also will be sinusoidal, but it will be a difference in which the supplied voltage minus generated back EMF in each coil. That voltage divided by the coil impedance will be current flowing to the particular coil, resultant current. That current generates resultant magnetic flux. That flux will going to attract the rotor magnet. So that's how both the coil. In case of BLDC, it will be a trapezoidal nature apply voltage because we are using the trapezoidal winding, which is called a concentrated winding. To obtain the maximum torque at best performance a given motor, the stator coil drive current should match the back EMF voltage. That's what I told you. If it is a PM, SM, the back EMF is sinusoidal. Correct? Back EMF is sinusoidal. So the current also should be sinusoidal. The winding is distributed. In case of BLDC motor, the stator coils are concentrated winding. So if I then it will produce the generated back EMF will be trapezoidal nature. So you need to supply the stator with trapezoidal current. Supplied current to coil also should be trapezoidal. Yeah, I'm going to show this one. So then only you will get maximum torque there. This one you cannot supply sine wave to the stator coil of BLDC motor like permanent magnet synchronous, that you have to remember. Then the trapezoidal drive sometimes is referred to as square wave drives. Correct? Some books they call it square wave drives because the stator will be supplied with a square wave, and when you supply a square wave, which is a pulse to a stator winding, which has an inductance resistance, this one, the current will be in the shape of trapezoid. So what you say square wave, many times you don't supply square wave, you supply what you called as modified or quasi square wave. I am going to talk in next slide. Okay, see here. If your motor, correct, I am talking about stator driving current. If motor is a permanent SM motor, what is winding type? Distributed winding. Distributed winding. Correct? If distributed winding, the back EMF generated due to rotor magnet. Rotor is a permanent magnet, correct? Rotor is rotating. That flux will cut by this coil, stator coil, because there's a back EMF generated. Since in permanent magnet synchronous motor, the winding is distributed, the back EMF generated will be sinusoidal in nature. That's what I'm showing here, blue color. Correct? In this case, what type of voltage you have to supply to the coil? This one, again, sinusoidal in the only. Correct? This is the IA supplied current or supplied voltage. If you supply sinusoidal voltage, sinusoidal current will flow, magnetic will flow. So this is the back EMF. So there's a difference between these two. Correct? I shown it bigger. This is this minus VS supply voltage minus V back. That means the difference. That means we have to show that this may be bigger. Correct? So then divided by Z will be the current that produce a magnetic flux. So that is for synchronous motor. Now, if we have, right now we are talking about BLDC motor. BLDC motor should be supplied with square wave. Square wave. Actually, current should be in trapezoidal. If you supply square itself, become a current will be trapezoidal. Square wave you can supply. But to make not having a torque pulses, sudden changes, please know that if I supply a square wave, what happens? Here it is 0 volts. For this duration, 0 volts. Correct? This is voltage. Correct? I say that this is 100 volts. Correct? This is 100 volts. And from time t equals 0, say this is 1 second. For this duration, voltage is 0. Then suddenly for the one coil, I am applying 100 volts. I am applying for some duration. Correct? Instead of supplying this one. So suddenly, if you supply this one, you can see what is slope of the square. When the voltage rising, it is infinity. Correct? So this will create current spikes. It will create what you call as current spikes in the coil. Correct? spikes are not unwanted. If current spikes are generated, it will generate torque pulses, torque spikes also, correct? The spiking is not needed. I want a smooth torque, correct? Smooth torque is one. As the motor rotates to 360, 0 to 30, the torque should be flat. But if I give a square pulse like this, it will create sudden. This one will create voltage, current spikes and torque spikes. To avoid that, instead of supplying this kind of a pure square pulse, correct? What they do is the green one, sorry, the green one is the pure side. They supply what is called a modified square pulse. You can see that the light green, correct? That is the modified. This is what nowadays they are supplying to your. Sorry, I will use the green color. This is called modified, correct? You can see that the pulse is. Okay, well, sorry, made a small big say. Extremely sorry, very sorry. Square pulse is G, correct? So the duration, we know that this is one cycle. If it is a PMSM, very sorry, PMSM, we are supplying sinusoidal voltage. The back EMF generator also will be sinusoidal. That we know, which is in blue color. If it is a permanent magnet DC motor, BLDC, brushless DC motor, then what we have to supply is the square pulse, which is shown in green color, correct? So you know that this is called a positive half cycle sine wave. This is called a negative, similar to negative, correct? In sinusoidal. In this case, you can see that means you start from 0, one cycle ends here. So that means if you, instead of sine wave, if you drive with square wave, the green one, correct? So this is the pulse. And it starts at 0. This is the half cycle, positive half cycle for the BLDC motor, square wave. This is negative half cycle, correct? So if I give that, and wherever transition happens, there will be a sudden spike will be there because you are applying full voltage. Instead of that, what they do is nowadays they are supplying what is called a modified DC voltage, correct? Modified DC voltage shown in red color. Again, this is used for BLDC motor. BLDC motor, you can use any one of this. Instead of square wave, using this is better. We will see later this one. We can see that modified DC voltage for some amount of time, from time t equals 0, 0 volts only we are applying. After that, we are applying full voltage. Correct? We are applying full voltage for this duration. Correct? Again, it comes down. And again, it will be 0 for some time. This is the first half cycle over. Next half cycle also, we are not going to supply current immediately. For some amount of time, we call the phase angle. This is called 360 degree. The total phase is 360 degree. Correct? So, this is called as 180 degree. Half cycle is 180 degree. Correct? Now, in case of modified this one, this will be 30 degree. For 30 degree duration, voltage will be 0. This is 0 degree. Then 0 to 30 degree, 0 volts. Then for this much period, 120 degree period, you will supply the full voltage. Correct? Red color. Again, from here, that is 150 degree to 180 degree. Again, it will be 0 volts. You can see the half cycle. For the entire half cycle, we are not supplying square wave, which is shown in green color. Instead of that, we are supplying a modified square wave shown in red color. That 0 to 30 degree, 0 current or 0 volts. 30 to 150, that is 120 degree, we are supplying full voltage, red color pulse. Again, another 150 to 180 degree, we are supplying modified. If you supply that, the current flowing inside your motor will be trapezoidal in nature. It will be like this. Correct? Same thing you are doing with negative half cycle also. You can see that. So this is how it works. So negative half cycle also you can see that. So being a permanent magnet, this one, since permanent magnet, BLDC motor. BLDC motor is a concentrated winding. So the back EMF generated will be trapezoidal nature. So the current supplied to coil also will be trapezoidal. To create a trapezoidal current in BLDC motor, you will be supplying modified square wave. That will create a current which is trapezoidal in nature. So the magnetic flux also will be trapezoidal in the stator winding, that is supply this one, and the rotor magnetic will create back EMF. This one also will be also trapezoidal in nature. So net resulting magnetic flux generated by the stator field will be trapezoidal, which will attract the rotor magnet and make a smooth curve. Okay. Now, the net voltage applied across the stator coil is the difference between the supplied voltage minus back EMF voltage. Correct? Supplied voltage is already we have modified this one, but it creates a current which is nothing but trapezoidal nature. Automatically, that is equal to generation of the trapezoidal supply voltage. Correct? That will be subtracted from the back EMF, and that resultant voltage will be applied. So BLDC motor decide the BLDC motors are designed such that when they are running at rated speed, we knew that already in previous class that motor can run 0 to some maximum speed, 0 to 2000 RPM, 0 to 1000, 0 to 5000, 0 to the motor designer says. But that is called rated RPM, continuous rating. At rated RPM, the voltage difference between the back EMF and supply voltage will be such that it produces a rated current. When I take a motor, say a BLDC motor, they say the rated voltage 100 volts, correct? That means you are going to give DC 100 volt voltage to the motor stator coil in the form of the square waves, which in turn produce a trapezoidal current inside this one, correct? So that is going to attract the rotor, and the rotor back EMF this one. So what we'll do is the rated current will be supplied under rated torque. I say that this motor 100 volts, 10 amps current, rated current, and rated speed 1000 RPM, rated torque is 10 Newton meter. Correct? So at that time, we will see that the back EMF generate a differential voltage in the stator coil, which is going to drive a current, which is called a driving current. It's called rated current. It will be rated in nature. So up from low 0 to 1000 RPM, 1000 is rated RPM is up to that the current will be sufficient to drive, producing sufficient torque. Correct? Now, if the speed of the motor exceeds beyond 1000, correct? BLDC motor, if it exceeds the speed beyond the rated speed, what will happen? The back EMF will be more than the supply voltage. I told you the current I equal to V supply minus V back EMF divided by Z. Correct? V supply will be up to the rated 0 to rated speed. For example, 1000 RPM. The Vs will be higher than VBM back EMF. Correct? The number of the rotor coil and the permanent magnet field strength pi R. Correct? Rotor magnetic field strength and the number of turns in the coils in the stator coil decides back EMF voltage. If motor is running up to the back EMF speed, then the rated speed, the back EMF will be always lesser than. That means V supply will be greater than V back EMF. I can say V back. That will be greater up to rated. If the speed exceeds this one, back EMF will be higher. And the supply voltage will be this one. Now, what will happen? The injected current will reduce. So the net voltage reduce. So the current reduces. The torque produced by motor will be lesser. Many times, as I told, up to rated, the resultant voltage, I say that V resultant is, for example, it varies from 100 volts to maybe say 80 volts. Correct? The supply voltage V supply equal to 100 volts. Correct? The back EMF will start from 0 to, for example, 80 volts. Correct? 0 to 80 volts. Back that is at rated RPM. That is 1000 RPM. If the rated if motor speed becomes 1100, what will happen? The back EMF will become say 90 volts. What is difference voltage? Vs minus 10 volts. So the current will become, so the torque produced by motor will become, if motor speed goes around 1200, correct? That is above this one, the back EMF will become 100. So that's what, at very high speed, if the back EMF increases because high speed generated, the net voltage and the stator coil current all will become 0 because the back EMF will be equal to the supply voltage. Correct? Vs will be equal to V back. So this is 100. The back EMF also 100 at 1200 RPM. Note down, correct? This is rated RPM is 1000. At 1000 RPM, back EMF was 80 volts. But difference voltage 20. So motor produces sufficient voltage and sufficient torque. But now as I increase the motor speed 1100 RPM, 1200 RPM, at 1200 RPM, the back end become 100. 100 minus 100 will become 0. So the current is 0, static current. So the torque produced. So that means you cannot drive. This is how it works. Okay. So this point should be noted. As I told you, this one, there are, how will you, now that we know how it works, the BLDC motor, correct? What type of voltage should be supplied, what type of current should be supplied. And I told you we need to generate these waveforms, correct? The drive waveform should be generated by a controller, correct? And it should be generated at appropriate time. With respect to, we say that this is called as electrical, this is 0 degree, this is 180 degree, this is 360 degree for phase 1. For correct, for phase 2, this is 360 degree. For phase 3, one cycle represents 360 degree. Correct. We can see that they are shifted by some this one. Correct. 120 degree they are separated. You can see that each this one waveform is separated by 120 degree. This is starting. This is the starting of second. This one. This is starting of the third phase voltage stator coil current. So they are all separated by 120 degree. Correct? They are all separated by 120 degree. One cycle is called a 360 degree. That is 1 off plus 1 on. On plus off. On plus off for any phase. 360 degree. We know that. Correct? So how do you know? That means whenever the rotor is within the 360 degree, correct? That time only we have to generate this voltage, correct? So how the controller, who is generating? This is generated by the motor controller. Motor controller, you may use microprocessor something or electronic circuit, which has to generate exactly like this, based on the position of the rotor. So how do you know the position of the, how the controller knows the position of the rotor? So that is done using sensors, correct? That is done using sensor. Or there are two types of sensing rotor position. One is using position sensor. I told you Hall effect sensor, correct? Hall effect sensor will be a sensor will be physically put on 3 locations, correct? It will put on 3 locations. That is 120 degree. This is HA sensor. 3 sensors are there. These sensors will generate pulses whenever the magnet, north pole of rotor, correct? North pole of this is north pole, south pole. If whenever north pole comes near that sensor will produce. That is also for 120 degree. Correct? The magnetic flux from the rotor, north pole will be going like this. Correct? So as long as the rotor is within this 120 degree, it will produce a pulse. So that means you can physically put 3 Hall effect sensor located near the stator, between the stator coils, correct? Between the stator coils at 120 degree. Stator coils itself is 120 degrees spaced, right? Between 2 stator coils, center position put. So there are 3 this one. So you have 120 degree apart, correct? So this angle will be 120 degree. Okay. So this using the sensor signal, I know that rotor is current location is known by this sensor signal. So the controller generates the waveform and supply the voltage to the stator coil. So the current flows, attraction, everything happens. Otherwise, this is called sensor based. That means you need 3 sensor based control. Right? We need 3 Hall effect sensor to know the current position where the with respect to stator coils, where the rotor position, correct? Does one. Otherwise, if this that means you need to add 3 Hall effects and cost increases. This instead of that, I can sense the position of the stator north pole by sensing the back EMF generated. Back EMF is generated as the north pole of the rotating rotor comes near the coil. It generates back EMF. Just now we talked. That back EMF will be maximum when the rotor aligns exactly with the stator pole. Correct? When rotor aligns exactly with the stator, okay, whenever it aligns something like this, that time if we put this one, the Hall effect sensor produce maximum voltage. Correct? So that way, sorry, the back EMF will be maximum. Very sorry, this is back EMF based. So that means I don't need Hall effect sensor. So you can see the back EMF increases when exactly aligns the back EMF. That means I know the rotor has come in the center position. Then using this one, I generate pulse, and this one, how will you do it? For that only the circuit is shown here. You can see that there are 3 coils. Each coil back EMF is generated. E back. I say EA back, EB back, and EC back. Voltages are these voltages. This voltage is given to the comparator circuit. I think last time when mechatronics studied, correct? Op-amp can be used as a comparator. Comparator, 2 input plus and minus. Between one is called neutral. With respect to neutral, the input voltage is given. So it generates a pulse. This pulse will be given to the motor controller, which in turn generates the IA current, supply current, which is injected to the stator coil accordingly. So this is based on back. What is advantage? I don't need the sensor. Cost effective. Correct? Using the back EMF, which is definitely in rotor, the rotor generates a back EMF in the stator coil. And when the stator aligns with the rotor coil, the back EMF is peak. If I detect this peak using this comparator, I know whether the rotor has come closer to the stator coil. So automatically, I can switch off this coil and give the power to the next coil. So the rotor will be pulled by the coil, goes to next. So that coil will give one after another. They will give pulses. Using this, you can generate this one. This is called as sensorless. Please note that this is called as sensorless BLDC motor control. Correct? It doesn't use Hall effect sensor, but it uses the back EMF which is automatically generated in the motor. So this, what is advantage? Cost effective. You are less by buying 3 Hall effect sensor that can be reduced. You may say, sir, wow, each sensor may cost 1,000, but if you are making the BLDC motor and selling per year, per month, you may make 1 lakh motors. Big manufacturers, they say, oh, 10 lakh, 1 million also they're supplying per month. Correct? Each Hall effect sensor costs even $2. Correct? Or $1. Or 3 sensors into $3 into 1 million, $30 million you can save in a year. Correct? So, like that. But of course, you will be using op-amps. The main problem here is you are going to use op-amp circuit. This also increase cost. We have to see whether Hall effect sensor. Hall effect sensor also need an amplifier. Hall effect sensor also need an op-amp. And just using Hall effect sensor, the op-amp comparator, you can detect the back EMF position and you can do that. So you compare whether the sensor with the amplifier is costly or this is better. Generally, back EMF based control will be simpler because you are less by the Hall effect sensor. Okay, these are 2 techniques. Now, back EMF crossing detection is the simplest thing. As I told you, 2 types of control is that Hall effect based, sensor based control. Other one is back EMF based. This is called as sensorless control. This is called sensor based control. Correct? You can call it sensor based, sensorless control. Correct? So this is cheaper comparatively, but there are some issues. Correct? If you want to deal, you can see that we don't have time because we cannot discuss anything for more, and we have to cross next class. We have to something else. Okay. So simplest method for back EMF sensing is back EMF based detecting at the individual where in the unexcited phase. Okay, we are going to see that. At zero crossing, the electronic commutation occurs. Whenever the let me go to the waveform, then you will understand. Okay, please see this waveform. I'm explaining you both this one. One is Hall effect also. You can see the 3 Hall effect sensor. Other one is back EMF. So the blue color is the back EMF. Correct? Back EMF for the A coil, back EMF of the B coil. There are B coil, C coil. Because you know that BLDC motor 3 coils. So then the green waveform is for the phase A, 3 phase. current injected. This is generated by the controller. Please note that the motor controller generates this waveform and supplies. What is this? This is a modified waveform. Generates modified square waveform. This waveform is generated, supplied to the stator coil voltage. Because of that, the current flowing that will be trapezoidal nature. Current will be almost like this, trapezoidal. If you apply voltage, the current will be trapezoidal. So modified voltage is applied. Okay, we can see that. That is one thing. Then this is called phase detector. Correct? We talked about this is called as phase detector. What is that? This is called as phase detector. Correct? This is supplied with these two voltages. Okay. Now, which is supplied? The back EMF voltage generated in the stator coil due to rotor magnet is a trapezoidal shape back EMF. This will be, because this is called zero value, correct? The value of the back EMF is varying 0 to positive voltage and negative voltage. So it is increasing from, let me use blue color, you understand. So it is increasing from minus voltage, increasing. This point is called a zero crossing point, correct? Then it goes to positive. So this point is detected, and whenever the trapezoidal back EMF of the BLDC motor crosses from negative to positive at zero crossing, that is called zero crossing point. Immediately the circuit, this circuit generates this one. You can see that it goes. The output will become 0 to 5 volts. Correct? So for example, the output is 0 to 5 volts. Now, how long it is going to be there? You can see the black color one is the output of the zero crossing detector. It goes up, remains 0. Again, when it becomes 0, you can see that when the back EMF start coming back, it goes to maximum, remains flat for some degree, 120 degree. Then it start coming because the rotor is rotating with respect to stator coil, A coil. So it is coming from positive to negative. Again, it crosses this one. This is zero crossing point. Again, you can see that the output of the phase detector becomes 0. Correct? So this is the phase detector output. This will be supplied to the motor controller. Correct? Motor controller, which in turn generate the waveform, the green color waveform, the current voltage waveform applied to. This is generated based on this zero crossing detector. You understand how it works? Any doubt? Please know that an exam it is expected. With the waveform, you have to explain. If you have any doubt, please ask. This is fundamental working of BLDC motor. Okay, so this is for one phase. Same thing happen each phase. Correct? For each phase, you can, if you see that for each phase, this is the supplied. The green one is the supplied current, injected current by the coil, stator coil, which is generated by the motor controller. And the blue color one is the back EMF generated in the stator coil by the rotor, which is in trapezoidal nature. And that is given to the phase detector circuit, which I shown in the previous this one. Right? Note down, this is this one. This is a coil A from with respect to center point. Correct? The voltage is given. This is called a reference point, 0 point. Correct? 0 volts. This is the trapezoidal voltage is given. So whenever this crosses this points, this generates a pulse. Correct? During these two points, this controller generates this pulse. This is given to ECU or motor controller, which generates the distributed one. Correct? This is for phase A. Same thing happens. But please see that each one is separated by some distance. Correct? So this is the first phase. And this is called a 6-step commutation. Correct? The board, you can see that I given, this is step 1, S1. Each step is for 60 degrees. This is 60 degree. You can see that there are dotted lines. Correct? So this is one step. This is the second step, 60 degrees, 60, 60. This is the last 60. So totally, this will be 360 degree. correct? Totally within 360 degree, you can see that the voltage, correct? Voltage supplied from 0, it goes to some voltage, say maximum voltage of motor, correct? Then it remains there. For this is for 30 degree. This will be 120 degree. Again, this will be 30 degree. Again, this is 30 degree. This is 120 degree. And again, this is 30 degree. You can see that within one cycle, this is called a one cycle, correct? This is one electrical cell, 360 degree. We can see that the voltage supplied to stator will be 120 degree period, it will be high, correct? Voltage is supplied. Then voltage comes to 0. It remains 0 for 60 degree, correct? 30 degree plus another 60 degree 0. Then it goes to negative voltage, correct? Negative voltage and remain 120 degree period negative voltage. Again, it becomes this one. So the cycle completes. Same thing happens each phase, correct? With shifting by 60 degree, correct? So you can see that this is starting of the this one ending for the coil A. When you same thing, if you see here for the second phase, it starts here, it ends here. For the third coil, starts here, end here. At different phases, you will see that different voltages applied. So when this is positive voltage, B is negative voltage, correct? C is floating. C is, you are not supplying any voltage. C is floating, correct? So we will see that different voltages applied and it generates. During the time, you can see that this is, that means if I want to use the sensorless control using back EMF voltage, back EMF alone, I don't need this. Okay. But if my motor is fixed with the Hall effect sensor, the Hall effect sensor, you can see that Hall effect sensor A senses this for how many degrees? This is 60, this is 60, this is 60, correct? 180 degree, the Hall effect sensor output will be high. And from up to this, for first 120 degree, the second Hall effect sensor output will be 0, but the third Hall effect sensor for 60 degree is high. You can see that for first 60 degree, this is high, this is high, this is 0 volts. For next 60 degree, this is high, this is 0, this is also 0. And third, this one, this is high, the second Hall effect will be high, third one is 0. Correct? This is 0 volts. Like this, for entire cycle, if you see that, please see that you take entire 360 divided into 60 degree phase angle. They call electrical phase angle. So, like by doing this, I can generate based on this signal if this voltage or supply voltage, correct? Stator supply voltage is generated, then it is called as Hall effect sensor based control. Instead of that, if I use this, it is called as phase the back EMF based sensor based this one. Any doubts? Okay. One small thing I just wanted to announce today. We announced exam is on 23rd, Sunday, correct?
Correct, sir.
23rd, correct? Yeah. Unfortunately, on the 22nd and 21st, I have some very important this one, that week, entire week. So I will not be able to conduct exam at 23rd. We will be shifting by 1 week. Very important, this one I cannot avoid it. Very, very important for me, an assignment. On 22nd, 21st I have. So for that I need to prepare a lot of things. So this, our midsem will be shifted by 1 week, next week. But portion will be up to the brushless DC motor. The brushless DC motor, little more is there. I will stop today. Already time up. Next class, Monday, I will complete this. That portion. Yes, please.
Sir, How much it's there, sir, for BLDC motor?
The BLD is over. The little more only. After that, some more equation, application, some that's it. Another 6 slides only.
So maybe we can conduct tomorrow, sir. Or Monday only, sir. No problem, sir. We will take it up Monday.
Yeah, Monday I will give, but the exam will be not on 23rd, it will be on 30th.
So
Got it, sir.
30th we have sir, sorry to disturb.
No
30th
problem,
we
no
have
problem. Please tell.
yeah, 30th we have IC engines exam, sir.
Okay.
Maybe on the Saturday can we have it? The 29th.
Yeah, 29th you will have exam. Okay, very good. 29th Saturday we will have this exam.
The
Yes,
IIT
sir.
campus, sir.
Yes, please.
Sir, this is in campus, sir. Exam is in campus, sir.
Yeah.
Okay, sir. Okay.
But no, this will be like online exam.
Yeah, it's an online exam.
No. What did you decide?
It's
Online
online,
only,
sir.
sir.
Like, yeah, we have decided for online, sir.
Oh, okay. Because last week you had exam. Because no, I had totally forgot. That's why I just asking. What do you
Okay,
want?
yeah.
You want to have online exam? Come to here center.
So we will have online only, sir.
But
Online
NSEM,
only, sir.
NSEM will be definitely.
For exam, all are agreed, sir.
Huh.
From our batch, all are agreed for to come to IIT, sir. Directly.
Okay. Anand is conduct online.
Yes,
ICG?
sir. Yes, correct, sir. Online,
Yeah.
sir.
Yeah. Okay, I remember. Yes. Midsem exam. I told you, correct? I told you online only, correct?
Yes,
Yes,
sir.
yes,
You
sir.
told online, sir.
Okay, fine. Okay. That will be on Saturday,
9.
29, online, 90 minutes. Okay. The portion be
Okay.
till I complete BLDC motor. Okay. That I will take one more class to complete application something, that's it only.
Right,
Okay.
sir.
Okay.
Sure, sir.
Thank you. See you on Monday.
Thank you. Thank you, sir.
Thank you. Please
Thank
give
you,
your
sir.
attendance before leaving without forgetting.